There is a lot hiding inside a sentence you've probably said with total confidence. Maybe while a kid traced a finger across a world map. Maybe under the pressure of a trivia scoreboard. Maybe with a paper map open on a cafe table. The highest point on Earth is Mount Everest. Now imagine a surveyor on a windy ridge, jacket snapping, a GNSS receiver bolted to a tripod, hearing you say that and not smiling. Not because you're wrong, because you're only right in one measurement system. And in the one that describes Earth's actual geometry, Everest loses. The point of land farthest from the center of Earth is not Everest. It's a dormant volcano in Ecuador called Chimborazo. If that feels like an attack on a childhood fact, good. That's what it sounds like when a simple story meets precision. Everest still holds the title most people mean. It is the highest point above mean sea level, 8,848.86 meters. Refined in 2020 after Nepal and China completed a joint survey and agreed on a figure that looks absolute in a headline but isn't. Chimborazo is only about 6,263 meters above sea level, more than 2 kilometers lower. Yet its summit sits farther from Earth's core. How can a shorter mountain be farther out? Because the Earth you picture, a perfect sphere wrapped in a neat, smooth ring of sea level, is not the Earth your GPS is measuring. And that difference isn't trivia. It's rotation, gravity, reference frames, and a planet that refuses to be tidy. Start with a word we throw around like it's obvious. Sea level. Sea level is not a smooth shell. It's not even stable. In geodesy, the science of measuring Earth's shape and gravity, the reference surface is the geoid, an irregular, gravity-defined surface that approximates global mean sea level. It bulges and dips because Earth's mass is uneven. Mountain ranges, deep ocean trenches, and dense structures in the mantle all tug on the oceans, and the oceans obey. So when Everest is reported as 8,848.86 meters, that height is tied to a specific vertical datum linked to the geoid, updated with modern satellite and ground surveys. It's a carefully produced number, not a tape measure result. And that's where the trap is set. If highest means farthest from the center, you're assuming the baseline, Earth at sea level, is the same distance from the core everywhere. It isn't. Earth spins. Over geologic time, that rotation has pushed the planet outward at the equator and flattened it at the poles. The result is an oblate spheroid, not a perfect sphere, but a slightly squashed one. The numbers are not subtle. Earth's equatorial radius is about 6,378.137 kilometers. The polar radius is about 6,356.752 kilometers. That's a difference of roughly 21.385 kilometers. 21 kilometers. Bigger than Everest itself. So picture two people standing at sea level. One is near the equator. One is closer to the poles. The person near the equator is already farther from Earth's center before climbing anything. Same sea level, different distance to the core. Chimborazo sits at about 1.5 degrees south latitude, almost on the equator, riding the planet's outward bulge. Everest sits near 28 degrees north, where the radius to sea level is smaller. Everest starts closer in, then climbs higher. Chimborazo starts farther out, then climbs lower. Add each mountain on top of its baseline, and Chimborazo ends up farther from the center. This is not a clever word game. It's measurable. Using the standard Earth reference ellipsoid, WGS-84, the World Geodetic System used by GPS, geodesists compute the distance from Earth's center to a given latitude on the ellipsoid, then add elevation using a chosen height model. The exact totals shift slightly depending on whether you reference the geoid or the ellipsoid and which elevation dataset you use. But the ordering holds. Chimborazo's summit is often sighted at about 6,384.4 kilometers from Earth's center. Everest's summit comes in around 6,382.3 kilometers, roughly 2 kilometers closer. 2 kilometers is not a rounding error. It's a clean, uncomfortable gap. If you're wondering who actually measures this and how, the answer is with a pipeline that's more fragile than the final number suggests. A GNSS receiver, GPS, GLONASS, Galileo, Beidou, doesn't directly give you height above sea level. It gives you height above a mathematical ellipsoid, a smooth, idealized shape that's convenient for computation. To get the elevation people recognize, orthometric height, meaning height above the geoid, you apply a geoid model. EGM 2008 is a widely used global model, with newer regional refinements in many countries. That conversion depends on gravity data because the geoid is, at its core, a gravity map. Then come the corrections. Dual-frequency GNSS helps reduce ionospheric errors. Atmospheric delays have to be modeled, including water vapor, especially punishing in mountainous and equatorial regions. Survey teams often post-process their data to squeeze uncertainties down to centimeters, using carefully controlled reference stations and long observation windows. And even after all that, the ground under the tripod isn't still. Everest's 2020 update is a case study in precision colliding with reality. Nepal and China combine GNSS observations, ground-based leveling, and gravity measurements to refine the summit height. They also had to contend with uncertainties that don't fit neatly into a headline. Snow and ice thickness at the top, seasonal variation, and a mountain range that is actively deforming. The Himalayas are a collision zone where the Indian plate is pushing into Eurasia. Everest can shift by millimeters to centimeters per year depending on tectonics and seismic events. The 2015 Nepal earthquake, magnitude 7.8, triggered widespread deformation and forced renewed scrutiny of benchmarks and vertical datums across the region. You can see it in the cracked buildings and landslide debris. The reminder that ground truth is not a static thing. Chimborazo isn't easy either. Volcanic summits can have complex topography, and equatorial humidity can distort GNSS signals if it's not modeled correctly. Chimborazo's advantage in this contest isn't better rock or better weather. It's simply that the planet beneath it is fatter. This is the moment most people miss. We're not arguing about which mountain is really taller. We're uncovering how many different questions we've been collapsing into one. There are at least 3 superlatives that can all be true at the same time. Highest above means sea level, Everest. Farthest from Earth's center, Chimborazo. Tallest from base to summit, often argued to be Mauna Kea in Hawaii, which rises more than 10,000 meters from the ocean floor to its peak. Even though its summit is only 4,207 meters above sea level. Different baselines, different answers, same planet. So what changes when you learn this? Not the mountains, the language. Once you understand reference frames, you start seeing how easily facts drift when the definition is left unstated. National mapping agencies are already updating vertical datums, moving from older tide gauge-based systems to GNSS and geoid-based systems. When that happens, official elevations can shift by tens of centimeters to more than a meter without any mountain physically moving. That affects engineering, aviation, flood modeling, and disaster response, because those fields run on numbers tied to reference surfaces. Meanwhile, satellite gravimetry missions like GRACE and GO-CE have mapped Earth's gravity field with unprecedented resolution, improving geoid models and turning sea level into something you can compute rather than imagine. As those models improve and as climate-driven changes in ice mass and sea level alter Earth's gravity field, more public-facing numbers will be revised. The confusion will grow, especially as consumer devices report altitude that may be ellipsoidal height, a coarse geoid correction, or something in between. In mountainous terrain, that can mean errors of dozens of meters. The device isn't lying. It's answering a different question than you think you asked. And then there's the phrase everyone loves because it sounds like a victory lap: closest point to outer space. Chimborazo, being closest to space, is a rhetorical shortcut for farthest from Earth's center on land. Outer space as a boundary is usually framed by the Kármán line at 100 kilometers, far above any mountain on Earth. Chimborazo doesn't get you meaningfully closer to orbit. It just wins a specific geometric contest on a planet that isn't a sphere. So here's the question, and it's not as harmless as it sounds. When science gives you multiple correct answers depending on definitions, highest above sea level, farthest from the center, tallest from base, do you want one clean story that's easy to repeat, or the precise truth that forces you to ask every time? Measured from where? What do you think?